In this video, I'll introduce power sources. Power sources create electrical power, usually from a non-electrical source. There are a variety of different types of power sources. In this video, I'll talk about both independent and dependent power sources. Power supplies provide electrical power to our circuits. Usually, the fundamental source of the power is non-electrical. For example, batteries convert a chemical reaction to electricity, and turbines use fluid flow to turn a generator which creates electrical energy. Power supplies are active circuit elements, so we don't have to use the passive sign convention for the power supply voltages and currents if we don't want to. There are a variety of different ways to model power supplies. Engineers will generally choose the simplest model that's appropriate for a given physical power supply. Power sources can be considered to be either current or voltage sources, based on the primary parameter they provide to the circuit. Batteries, for example, are generally represented as voltage supplies, since their voltage remains constant over a fairly wide range of currents. Sources can also be categorized as either independent or dependent. Dependent sources provide power that's controlled by a voltage or current elsewhere in the circuit they're powering. On the other hand, independent sources are not directly controlled by the voltage or current elsewhere in the circuit. Finally, sources can be either ideal or non-ideal. Ideal sources don't exist in reality, but they can be a useful approximation in many cases. For the rest of this video, I'll talk only about ideal, independent voltage and current sources. These are the simplest power supply models, but are useful in a wide number of cases. First, I'll talk about voltage sources. These are three common symbols used to represent ideal independent voltage sources. In all cases, the voltage being supplied is labeled next to the symbol. This circle with the plus and minus sign inside it is used to indicate either a time-varying or a constant voltage. The plus and minus signs indicate which terminal has the assumed higher voltage. This symbol is for a constant voltage source, usually interpreted as a battery. The longer line has the higher voltage. Finally, this arrow also indicates a voltage source. The voltage value is usually taken to be relative to ground, which will be labeled elsewhere on the circuit schematic. The main property of ideal independent voltage sources is that they provide the specified voltage regardless of the current demanded of them. This means that we don't know anything about what current's being provided by the supply until we connect it to a circuit. Now let's look at the voltage-current relation for an ideal constant voltage source. For this case, the voltage is just a constant value, V sub S, regardless of the current. This is a plot of the voltage as a function of current. Since the voltage is constant and does not depend on the current, this is a straight horizontal line. We don't know anything about the current directly from the properties of the source, so we don't have a functional relationship between voltage and current for an ideal voltage source. We don't even know whether this current is positive or negative. This means that we don't necessarily need to obey the passive sign convention when defining the current for that type of source. This is the symbol for an ideal independent current source. I'll use it to represent both time-varying and constant current sources. An ideal independent current source provides the displayed amount of current regardless of the voltage difference across the current source. The voltage-current characteristic for an ideal independent current source looks like this. The voltage is independent of the current and can take on any value. We don't even know anything about the sign of the voltage. It can be either positive or negative. As with the voltage source, we don't need to obey the passive sign convention if we define the voltage across the current source, since there isn't a functional relationship that relates the voltage and the current. It's important to remember that the ideal independent sources in this video are only mathematical models that approximate the behavior of actual sources. A model of a circuit element will have limitations that make it behave differently from a real element. Our goal when modeling a circuit is to choose the simplest model that adequately describes the behavior of the real element. One obvious problem with ideal sources is that they can deliver infinite power. Since an ideal voltage source can provide any current, the current can be infinite, which is impossible for a real device. Likewise, since an ideal current source can provide any voltage, the voltage can be infinite, which is also impossible. So depending on the circumstances, these models can be unrealistic. Therefore, the underlying assumption when using an ideal source is that its actual current or voltage will be low enough so that its behavior is close enough to ideal. There are fairly simple approaches to modeling sources that do have limited power output, and we'll see some of those later in this course. Independent sources provide a specified voltage or a current to a circuit regardless of the circuit itself. Dependent sources adjust the voltage or current they provide based on a voltage or current somewhere else in the circuit. As with independent sources, dependent sources provide power to a circuit. However, unlike independent sources, dependent sources adjust the power they provide based on conditions in the circuit itself. Since dependent sources provide power from a source external to the circuit, they are active circuit elements. But the voltage or current they provide is controlled by a voltage or a current within the circuit. Symbols representing dependent sources are shown here. The dependent source is indicated by this diamond-shaped symbol rather than the circle we used for independent sources. An arrow inside the diamond indicates a dependent current source, while the plus and minus signs indicate a dependent voltage source. As with independent sources, the arrow indicates positive current direction, and the positive and negative signs indicate the voltage polarity sign convention. Since the source can provide either a voltage or a current, and the source can be controlled by either a voltage or a current, there are four possible types of dependent sources. A voltage source that's controlled by a voltage elsewhere in the circuit is a voltage-controlled voltage source. A voltage source controlled by a current is a current-controlled voltage source, usually abbreviated as CCVS. A current source that's controlled by a voltage is a voltage-controlled current source. And finally, a current source that's controlled by a current somewhere else is a current-controlled current source, or CCCS. Here are a couple of examples of dependent sources. This one is a voltage-controlled voltage source. The circuit symbol indicates a voltage source, and the voltage it applies is some number, K, times a voltage elsewhere in the circuit. So it's a voltage source that's controlled by a voltage. This is a voltage-controlled current source. The current that the source puts out is based on a voltage somewhere else in the circuit. There are a variety of common circuit components that behave like dependent sources. Transistors, for example, appear nearly everywhere. One category of transistors is metal oxide semiconductor field effect transistors, or MOSFETs for short. A common use for MOSFETs is to implement the switching operations that make computers work. Fundamentally, they tend to behave like voltage-controlled current sources, though they can be made to behave like other types of dependent sources with external circuitry. Another type of transistor is the bipolar junction transistor, or BJTs. These are often used in amplifier construction. Operational amplifiers are super useful devices, as we'll see later in this course. They're constructed using MOSFETs and BJTs. One really neat thing about operational amplifiers is that they can be used to build circuits that perform mathematical operations, which is the source of their name. So you can easily implement operations such as addition, subtraction, multiplication, integration, and differentiation with operational amplifier-based circuits. Finally, let's take a look at a circuit that uses a MOSFET to implement a dependent source. This is the circuit symbol for a MOSFET. It has three terminals: a gate, a drain, and a source. When the gate voltage, VG, is low, the MOSFET does not allow current to flow from the drain to the source. If VG is high, the MOSFET does allow current to flow from the drain to the source. Current through the MOSFET is being controlled by a voltage, so this is a voltage-controlled current source. Since the circuit's an active component, it provides power from an external source. I'm using a 9-volt battery to provide power. This dependent power supply requires an independent power supply to function, which in this case is the 9-volt battery. The circuit's controlling the current leaving the battery based on a voltage applied to the MOSFET. Now let's implement this circuit and see how it works. I want to use my analog discovery to turn this motor on and off. Unfortunately, the analog discovery itself doesn't put out enough power to turn this motor. So I've created a dependent source that's controlled by the analog discovery. This 9-volt battery provides power to the drain of the MOSFET. The source of the MOSFET is connected to the motor, which is connected to ground, and channel 1 of the analog discovery is applied at the gate to turn the MOSFET on and off. So when this voltage is low, no current flows to the motor. When this voltage is high, I get to flow current from the battery to the motor, and it turns the motor on. So right now, the voltage is 0 and the motor's off. Let's change that voltage to a high voltage, 5 volts. That turns the motor on. Going back to a low voltage, turns the motor off again. That's all I want to say about dependent sources for now. I'll talk about dependent sources again later when we do amplification. Also, if you take a later class in electronics, you'll model transistors as dependent sources. The next video is about resistors. Resistors, unlike sources, have a functional relationship between voltage and current at their terminals. That relationship depends upon the passive sign convention. If you're unsure about the passive sign convention, it'd be a good idea to go back and review that before you go on to resistors.